Hi everyone from Cosmology from Home. My name is Lemos. I will present here my work called untitled as Cosmological-Model-Independent limits of photon mass from FRBs and supernovae data. This paper was in collaboration with these people here. But before I start to talk about the paper, some information about me. I finished my PhD in the end of the last year, and I started my first postdoctoral at the beginning of this year, both in the National Observatory in Brazil, more precisely Rio de Janeiro. These papers are in the archive, so everyone can access use this QR code here. And we submit this paper for GCAP. Now we write the answer of the referee. The invariance of the speed of light, basically the constants of the speed of light in vacuum for any observer in any frame, is a fundamental postulate in Einstein's special relativity and of course in general relativity too. This postulate indicates that the photon should be massless, so any evidence for a mass, photon mass, leads to a new physics, is an evidence for a new physics beyond the special relativity or general relativity. In a scenario with photons with mass, the group velocity will depend on this energy of the photons with mass, and you can see in this case you see that photons with high energy will be faster than photons with low energy. So basically two photons emitted at the same time for the same source with different energy will reach the Earth at different times. So we'll see a time delay between these photons. So you can use astrophysical source with emit photons with different time to test photon mass. So you can, in this case, we are using a radio astrophysical source that have a special measure observed from the source to test the photon mass. In our case, we are using FRBs, fast radio bursts. The FRBs are transient radio event. It means that the energy of this event will decrease with time. This event has a high energy, a short duration in the frequency of the radio. The first burst was discovered in 2007, and since then we observe almost 1,000 events. But although we observed many events, we don't have a lot of information about these events. We don't know the progenitor of this event, and we don't know the radio mechanism of this event, the radio emission mechanism of this event. But we have some informations. And the information that we have is related to the dispersion of the radio waves. So the radio waves will be dispersed by the plasma. Photons emitted from the source with a high frequency, you reach the Earth first, then the photons with the low energy, low frequency. And this difference of time, this time delay, can be related to this quantity here, called as the special measure, dm. And dm is the integral of the density of the free electrons along the line of sight. And from the special measure, we have some information about the FRBs. The observed special measure, so basically the total special measure observed directly from the source, is greater than the Milky Way contribution. So we have that FRBs has extragalactic or cosmological origin. So the goal of this paper is to constrain the photon mass, so test if the photons are massless using a cosmological-independent method. That we have some papers using this very similar method, where we combine the FRBs with the supernovae data. So we write the equations of the special measure, and we will combine this special measure of FRBs with the luminosity distance that we calculate from supernovae data. Here's some theoretical information about the FRBs, but a very quickly information about the FRBs. As I commented before, the photons with high energy, high frequency, you get the Earth first, the photons with low frequency. So the photons from the source will interact with the free electrons in the medium, and these interactions leads to a change in the frequency. Change the frequency, you change the velocity. So we have different velocity for each medium. So we can write the dispersion measure, the observed dispersion measure of FRBs, as a contribution of each medium. So in this case, we can write like the contribution of the Milky Way, IGN, and host. The Milky Way contribution is a combination of interstellar medium and halo, where the interstellar medium contribution can be very well constrained using pulsar observations, and the halo contribution can be assumed with some values, and in our case you consider being this value here. And the host contribution, the M host, is a very poorly known parameter. We don't have a lot of information about this quantity because it's very difficult to measure and very difficult to model. Depends on many factors of the galaxy, host galaxy, and in this case we can write this the M host being like this, where 1 plus E is related to the time dilation, and the M host not is a free parameter in our model. And the last term, the MIGM, is the average of the interstellar medium contribution, can be written like this, where HZ is the Hubble parameter and FIGM is the baryon fraction in the interstellar medium. And from this equation here, we can see that FIGM and HZ are degenerated parameters. So usually many papers on literature assume some cosmological model to constrain the FIGM. Now, I will present here our method that you will develop to constrain the photon mass. And first, you need to consider a scenario where photons has mass. So you consider a scenario on non-zero photon mass, and we'll need to consider this non-zero photon mass in the dispersion relation equation. Now we will consider the dispersion relation with this term here, where omega gamma is related to non-zero photon mass. That depends on the photon mass, and gamma here. And we will now calculate the time required for the radio wave to reach the Earth from the source at a distance d, a distance s along the line of sight. And this time required can be written like this, where this time required will depend on the frequency of the photon mass, non-zero photon mass. And the omega p is the plasma frequency. Now we need to consider, in a cosmological point of view, basically we need to consider the FRB at a redshift z, and we will do some modifications in the previous equation. We will consider the observed frequency in the observed frame, and we will change from dt to dz the integral. So the time required now is given by this relation here. But the quantity that is measured is not the time required, but the rate change of the arrival time. So we need to derivate this expression here in terms of the observed frequency, and now you obtain this expression here with these two integrals here that you can see. The first integral is the dispersion measure relation that I showed before, and the second integral is related to the non-vanishing photon mass. So it's the term related to the dispersion measure for the non-vanishing photon mass. Now the observed dispersion measure of the FRBs can be written like this, where now we have this additional term here, that dm gamma, that is this integral here. Now we will introduce the two quantities, the extragalactic, the quantity called extragalactic dispersion measure, but we will introduce the observed extragalactic dispersion measure and the theoretical one. The observed is a difference between the observed terms, so it's the difference between the observed dispersion measure of the FRBs and the Milky Way contribution. And the theoretical one is the remaining part, the remaining terms, so it's the assumed between host, IgM, and dm gamma. Now, related to the MIGM, as I showed before, the MIGM is written like this, where we have this integral here, where HZ and FIGM are degenerated. FIGM is a polynomial parameter. We have some simulation and numerical works that found some value for this parameter, but is not very well constrained. So we need to assume a cosmological model in the HZ, or you need to a model independent method. In our case, you use a cosmological model independent method that we use in a previous paper that you publish. So you solve this integral key by parts, where we use the definition of luminosity distance, and in the end the MIGM will be right like this. Now the MIGM will depend only on the luminosity distance and not will depend of the HZ. So in this case, in this equation here, the MIGM will depend on the DL that can be calculated using supernovae data or another measurement of distance. And the integral, now the equation related to the non-zero photon mass, this integral here is the same thing. We will solve this integral here by parts using the definition of luminosity distance, using the integral of the luminosity distance, and in the end you obtain an expression for the dm gamma that will depend only on the luminosity distance. And in the same case of the MIGM, you can calculate this DL, the luminosity distance, using supernovae data or another kind of measurements. And now about our methodology. First, I will talk a little bit about the data that you use. In the literature, you have almost 100 well-localized FRBs. It means 100 FRBs with the redshift, but we cannot use all of them because we have some points with some problems. So as you can see here in this plot, for example, this FRB here looks like an outline, so we remove this point, and we remove points with another problems like two different values for the redshift, and we remove the points that we don't have the uncertainty of the observed dispersion measure. And with the end, our remaining sample has 68 well-localized FRBs. In the case of supernovae data, we use the Pantheon catalog, that is a catalog of supernovae data with about 1,000 supernovae data, but we perform a Gaussian process of this catalog because we need to combine the supernovae measurements in the same redshift of the FRBs, but so it's more easy to do this in performing a Gaussian process of the Pantheon catalog. And some aspects in our analysis I need to mention here. We consider for the uncertainty of the intergalactic dispersion measure this expression here, where sigma OBS is the uncertainty of the observed dispersion measure. This term here is the uncertainty of Milky Way contribution. This one here is the uncertainty of the IGM contribution, that is can be calculated performing the error propagation of the expression that we find for the DMIGM. So basically this quantity here will depend basically from the luminosity distance uncertainty, the host uncertainty, and this delta here is I need to comment here is the fluctuation. So the inhomogeneity of the density of free electrons in the universe leads to a variance in the dispersion measure. So basically we have fluctuations in the value of the dispersion measure related to the inhomogeneity in the density of the electrons in the universe. So this fluctuation can be treated as a probability distribution function or as a fixed value. In our case, we will consider this fluctuation being a fixed value, and we follow some papers on literature and assume this fluctuation by this relation here. And you decide in our analysis to do two different approaches, to consider the FRGM being a fixed value, this 0.83, and in the second moment we will consider the FRGM being a free parameter, because you want to see the impact of the FRGM, the baryon fraction, in the constraints of the photon mass. Here are our first results. Here is the result of the photon mass and the DM host knot in the case that the FIGM is a fixed value. And we obtain the photon mass, this value here, and the photon mass is in this case in the kilogram. This value that we found is in concordance with 0 between 3 and 4 sigmas, so we obtain a very high value for the photon mass compared to the other papers on literature using FRBs and Cosmological-Model-Independent method too. But when you consider the FIGM being a free parameter in the analysis, the result that we found for the photon mass is a little bit different. Now we obtain the photon mass in concordance with 0 in between 1 and 2 sigmas, and this value here is very different from the others on literature, but especially the robar of your results is very different from the others on literature, but we have some idea that can be related to this difference. But I want to highlight something here in our results, that is this region here between the FIGM and the photon mass. As you can see here, the FIGM and the photon mass is very anticorrelated, as you can see here. And we're looking for on the literature and other papers to see if some authors mention this anticorrelation, but the other papers on literature assume the FIGM being a fixed value, being this value here. And this, we cannot say that where this anticorrelation comes from, but in our opinion, this anticorrelation can be related to the fact that the theoretical intergalactic dispersion measure depends on the dm IgM and dm gamma, where dm IgM is a function of FIGM and the dm gamma is a function of m gamma, the photon mass. So maybe this anticorrelation can be related to this equation. Now our conclusion. So basically in this paper we present a cosmological model-independent approach that you develop to constrain the photon mass, where we derivate the expression of the dispersion measure of FRBs, which we combine well-localized FRBs with supernovae data from Pantheon catalog. And our results, when we consider the FIGM being a free parameter in our analysis, shows an anticorrelation between the photon mass and the baryon fraction and the IgM. So is this. Thank you everyone, and I'm rating everyone in the section talk. So see you there.